In our last video, we took a look at the Lagrange Interpolating polynomial for a line when we just had 2 points. And so in this video, we're going to generalize that, and we are going to find the nth Lagrange interpolating polynomial. So the nth Lagrange interpolating polynomial. So we have this theorem to start with. Suppose we have these points x0 through xn. So how many points are there? Well, there are not n points because we also have x0, so there are n plus 1 points. And f is a function whose value at these points is given. Then there is a unique polynomial, p of x, of degree at most n, with f of x sub I being equal to the polynomial at those same x sub I, for I equals 0 to n. Right? So there's a unique polynomial that has the polynomial value agrees with the function value at all of these n plus 1 points. That polynomial, it is given by p of x is the function value at x0 times L0 of x plus the function value at x1 times L1 of x plus the function value at x sub n times Ln of x. Now, you might say, but what is that value? Oh, in fact, we will write this as, so here I've written the lazy person's notation. It is this, actually. We'll have n comma to identify that we have n different points, even though we went out to n. Yeah, we'll leave it there. We will shorthand that when the number of points is clear, and we will write something different. But how do we define lnk, right? So lnk of x, the way that that is defined is you'll have x minus x0 on top times x minus x1 times, multiply that all the way up to x minus x sub n and on bottom you will have xk minus x0, xk minus x1, xk minus x sub n. Now that's almost exactly right, except for there's one tiny thing that's not going to work out here, right? So the way I've written the top, this suggests that we have absolutely every value of x sub k subtracted on top. So when you plug in x sub k into that portion, that would just zero out completely. And so what we want to do is we want to omit. And so the way that you describe this omission, you can do that in a couple different ways. Here's the way I will do that. So instead of going all the way to here, we actually really need to stop here at x minus x sub k minus 1, and then jump over that one. So x minus x sub k plus 1, and then continue multiplying up all the way to x minus x sub n. And we need to do the same thing on bottom, otherwise we'd have a 0 in the denominator. So we'll have x sub k minus x sub k minus 1. We will skip over what would have given us the 0 in the denominator. And so the degree of this on top, the number of x's variables, we have 1, 2, all the way up through n. I guess we started with, our first one was at the 0. So we have n plus 1, but because we omitted that 1, we should actually just have n. So if the degree, this is what I started to write moments ago when I first wrote this down, if the degree of that interpolating polynomial is known, then instead of writing this as ln comma k, we'll just write it as lk. We will ignore the first number in that comma. All right. In the next video, we'll take a look at an example where we find an interpolating polynomial.